right, so test. Okay, hopefully everybody can hear that. All right, for those online, sorry about the delay. Having trouble with logging into the Canvas here. We're losing a few minutes. So today we're going to carry on with applications of Laplace transform. And in the previous lecture, we covered using Laplace transform to solve convolution. And also we demonstrated with a generic example how to use Laplace transform to solve a second order ODE. So today let's continue on the topic. Okay, so using Laplace transform to solve ODE. Now we'll look at a more detailed cases. So when you have an ODE, okay, so we typically say in our class we deal with the second order ODE. So your ODE probably y prime ay prime plus by and equal to f of t. So as we demonstrated from previous lecture, now if you take Laplace of both sides, okay, and then you will be able to obtain an expression for y of s, which is going to be a fraction. Okay, so y of s is Laplace transform of the system output y of t. So just bearing in mind, like this is side here is your input, f of t is input, and y of t is the output. Right, capital Y of s is the Laplace y of t. So if you take Laplace both sides and also based on certain given initial conditions, you will be at the end you will end up with a fraction for the y of s. And the idea is from here you want to simplify, right? So then you want to, let's not call it simplify, let's call it, so basically to transform the fraction into very simple form. Okay. We could say simplest form. Simplest form means the kind of format that you can actually look up from the Laplace table, okay? Or the simplest format exists in the Laplace table that handed out to you. So you want to transform this fraction into very simple form. And then the next step is you can look up table, right, and find the inverse of y of s. And the inverse of what? That's from outside? Yeah. And the inverse y of s, right, which is basically y of t. That's the idea of using this Laplace transform to solve ODE. Okay. So the key here, the first step is actually not too bad. So taking Laplace of both sides, if you use the property or use the typical Laplace property, then you will be able to get a fraction, and that shouldn't be too difficult. Okay. Now the key here is, this is a key here, is to transform this fraction into the simplest form, so that you can use a table to find the inverse. So that's the key here. Okay. So that's what I'm going to demonstrate in this class. I'll probably just demonstrate two cases. I think that should be enough. Okay. What are the typical format of this fraction for y of s? And then under that format, how we can do to simplify it or to transform it into the simplest form. So that's the objective here. Okay. So number case 1. Y of s has distinct simple poles. Okay, so if the y of s, which has the fraction like this, contains simple poles, so that's what we do. Okay? So here's the situation. Chances are you might end up with y of s looking like this. So you have a numerator, right? And the denominator, you can separate the denominator into fractions, into factors, okay? So I'm writing a very generic denominator here. So you can look at the denominator, there are n number of factors. So the polynomial for the denominator somehow under certain situation could be written as a multiplication of several factors. And each one of the factor, as you can see, we call it simple poles. It's just there's no high order, just to the order of 1. And we call this P1, P2, Pn. Okay. We said P1, P2 up to Pn. Those numbers, and they are distinct, so they're different. If some of the repeats, then it doesn't fall under this case. Okay, yeah. So technically, the poles for this y of s, okay, for this fraction, is negative P1, negative P2, and then negative Pn. So basically, if you let each one of the factor equal to 0, then you get a solution negative P1, negative P2, negative Pn. That's what we call poles. If you recall at the end of the previous lecture, the definition of poles is when you let the denominator equal to 0, the solution are called poles. So if y of s somehow could be written in this format, then I can rewrite this y of s into the so-called partial fraction expansion, basically. Into addition of very simple fractions. Each fraction denominator is actually part of the factor on the original fraction. Okay. So you can write this y of s into this format. This is essentially, sometimes we call it partial fraction expansion. The numerator here now has constants k1, k2 up to kn. So those are constants, which of course we need to find it out. P1, P2, Pn, they are from the original fraction. Now, probably I should see one of the things. There should be a condition, okay? So the degree of the polynomial of the numerator should be less than the degree of the numerator. So the polynomial for the numerator, let's say, is s plus 2, so degree of 1. Then the polynomial of the degree of the denominator should be at least 1 or 2. Okay. So now, how do I find this constants ki? Okay. How do I find this constant ki? There are a couple different ways you can do it, but there is one way is to use a formula. So you have a formula here you can help you to find this ki. Ki, each one of the ki equal to s plus pi and multiply by the original y of s, and then you let s equal to negative pi. So after you multiply s plus pi with y of s, for the rest of the expression, replace s with negative pi. And that's how you can get the constants for the numerator. Or somebody call it coefficients. Okay, so I'll show you an example next. So this is basically the first case. Okay, so let's take a look at example. Here is y of s squared plus 12 divided by s times s plus 2, and then times s plus 3. Okay. Now, if you observe this y of s, this is exactly the case 1 we're looking at. You look at the denominator, that's exactly the format. Right? So you have 3 factors multiplying each other, s plus 2, s plus 3. So if I ask you what's the pose for the system, the pose of the system, number 1, we call it s. Number 1 s associated with this. What's the pole for this one? 0. And the other one? Good. Right? So that's how you identify the pose. Although sometimes you probably don't really need that, but that's how you identify the pose. Once you identify this 3 different ones, then I can use the formula. So I know my y of s will be able to return into additions of those simple fractions. So I just have to calculate each one of the k's. So k1, k2, kn. Right. So let's write down y of s first. k1 over s plus k2 over s plus 2, and k3 over s plus 3. This is your final product y of s. For k1, I'm going to use the formula. It's s multiplied by y of s, and then replace s with 0. Okay, that's the pole, right? The first pole associated with it. And you can actually see the reason why you're multiplying by s first and then replace s with 0. So you see, if I multiply by s multiply s by the original expression here, so this s cancel, and you end up with just s squared plus 12, s plus 2, s plus 3, and then replace s with 0. And if you don't do that, if you replace s with 0, you actually end up with dividing by 0. It's like infinite, right? So now, so 12 over 2 plus 3, 2 multiplied by 3 was 6, so end was a 2. Similarly for k2, multiply s plus 2 first, and then s equal to -2. So that gives you s squared plus 12 over s plus 3. So -2 squared plus 12 over -2 plus 3. How does that work? So -2 is 16 over -2. You should get -8. That's k2 value. The last one, k3, s plus 3, y of s equal to -3. And then you get s squared plus 12 over s plus 2. Plugging into -3, so you should get a 7 for this question, for this k3. So finally, your y of s is 2 over s plus, oh, it's -8, so I probably just write a negative here. 8 over s plus 2, 7 over s plus 3. So this is the simplest form you can get based on this. So the reason is because if you look at the table that we handed out, the Laplace table, so you can look up a table now, but I think once you do a few more, so these simplest ones, you don't really need a table anymore. So basically, you will look at this one to find the inverse Laplace, right? For adding 1 over s plus 8, its inverse is e to the power -8t. And if you have a 1 over s, and its inverse is just a unit step function u of t, then for this question, if you look at this, so then my y of t, which is the inverse Laplace, right, at 2 over s, inverse Laplace and minus here, 8 over s plus 2 plus inverse Laplace 7 over s plus 3. So according to the table, the inverse of the first term should be 2 times u of t. And the inverse of the second term should be a times e to the power negative 2t. Now, just to jog your mind a little bit more here, remember what I said for this table, right? We consider every function is a causal function. So I did not write the function multiplied by u of t, but inherently, right, you should have a u of t there, so that the function itself become naturally a causal function. Okay, so for consistency, if you write a u of t here, then you should write a u of t at here. Now, if you don't write u of t, if you write a 1 at here, then you don't need to write a u of t. Okay, so everything else you can multiply by u of t. So then you can take the 2 out, you can take the u of t out. So it's basically 2 minus 8. All right, so this is the whole function. Now, if you don't multiply u of t, it's okay. Okay, so we can still consider it as the right answer. Yeah, the idea is basically you're dealing with a causal function here. Okay, so that's the method for function y of s, if it can actually be written in this format, right, for the denominator. Alternatively, if you happen to forgot the formula, for example, right, this is a formula for calculating ki. Okay, somehow you don't have the formula sheet and you forgot this ki, right? So then what do I do? How do I get this coefficient k1, k2, k3 then, right? So you actually can also do it by a very old traditional approach called comparing coefficients. Right? So how you can do that is this. Alternatively, I say use comparing coefficient approach. And this approach actually is more generic, as you can see if we cover another case, also apply to the other case. So here is the decomposed y of s. Okay, we're looking for k1, k2, k3. So what we do is we can write it back into the fraction. Okay, one single fraction, write it back into one single fraction. So that's k1 times s plus 2, s plus 3, k2 times s plus 3 times s, and k3 times s, s plus 2. You write it back into one single fraction, and this is how it looks like. Okay. And then you don't have to worry about the denominator, because the denominator is the same as your original denominator. But the numerator, right? You want the numerator to be the same as your original numerator, s squared plus 12. So what's my updated numerator based on the k1, k2, k3 then? So we multiply everything out and group similar term. Group similar term basically means associate the s to the power 2 terms together. So you're gonna get k1, k2, k3, and also associate all the terms with the s to the power 1 together. Of course, you have to simplify a little bit and you get this. So just try to calculate really carefully. Okay. So that's the terms associated with s. And lastly is a constant term, which only is a 6k1. Okay. And then this numerator, without a question, it has to be the same as s squared plus 12, because that's the original numerator. So now you compare coefficients. Compare coefficient basically means what are the coefficients for S squared? So here's K1 plus K2 plus K3. And the coefficient for the other side for S squared equal to 1. And coefficient for the S term here, 5K1, 3K2, 2K3. There's no S term on the other side. So then this whole term should equal to 0, exactly. And lastly, the constant term 6K1, right? This is S term. This is S to the power 0 supposed to be, right? So you can see the drop of the order here. So that should equal to 12. So altogether, you should get the same results. So K1 equal to 2, K2 equal to -8, K3 equal to 7. This is an alternative approach called comparing coefficients. You just have to write it back into single fraction and then start comparing coefficients of the left side and the right side and solve a number of equations. Good. Okay, so that's case number 1. When y of s contains distinct and simple poles, okay, so they're real poles actually. Okay. So case number 2 is when y of s has a complex conjugate poles. Complex conjugate poles. So let me show you one example here. So let's say suppose we're going to solve this second order differential equation. With initial condition 0, 0. So both of the position and velocities are 0. Right? If you're solving in time domain, to jog your mind, I mean, you look at the current f of t at here. Apparently, it's an exponential function, so you can use either the undetermined coefficient methods or use that variation parameter methods. Okay, both should work. But I'm going to solve it using Laplace. Okay. So that we take Laplace of both sides. Then we get s squared y of s. Okay. Laplace of a second order derivative according to the property is s squared pi multiplied by y of s minus s y of 0, then minus y prime of 0. Okay. Laplace of the first order is 8 times s y of s and minus 8 times y of 0. And then 25 y of s. And the whole thing equal to the other side. Laplace of this exponential is 1 over s plus 3. And that's the result of the Laplace transform. Now, because initial condition is 0, so this term is gone, so there's no contribution from initial conditions. Then what you're left with, right? You're left with this term, that term, and this term here. And you have a common factor y of s. So take out the common factor y of s, so s squared plus 8s plus 25 equal to 20 over s plus 3. So this is your simplified expression. Now, as you can see here, first word, okay, the resulted term associated with the y of s, s squared plus 8s plus 25. I think I mentioned this in the previous lecture. This certainly looks very much like the characteristic equation, right? So you recall, characteristic equation is lambda squared plus 8 lambda plus 25 equal to 0. A characteristic equation, the left side, is the same quadratic function as you have it here. And that's the contribution from your original second order differential equation. Then y of s equal to 20 over s plus 3 s squared over 8s divided by and then plus 25. Okay. So now you get a fraction for y of s. So this is in the format of a numerator divided by a denominator. Okay. So from here, of course, we're talking about a different case. But if you're presented with this result, and you need to proceed from here, then you actually have to identify, what kind of a denominator do you have over here? So this s plus 3 is a simple fraction, right? It's called simple pole because the pole here is s equal to -3. It's a real pole. So the question is associated with this quadratic s squared plus 8s plus 25. Now, of course, you would see kind of actually write this into a multiplication of two factors. Okay, and not only that, can I write it in multiplication two factors? The poles for each factor is a real, simple poles, right? That's the question. So you always have very easy to verify. Basically, you need to verify, right? If you set this equal to 0, what are the solutions, or what are the roots, or what are the poles? Is it going to be real ones? Is it going to be complex ones? Okay. So if the solution out of it turn out to be, let's say, for example, one is 2, the other 3, okay, so then you can actually write it into a s plus something multiplied by s plus another one. Okay, so that's what you need to verify at this stage. If you have a calculator now, you can also verify this, the solution for this one here, or is equivalent to the solution of the characteristic equation, basically. Okay, so you will find out the solution to this quadratic function is a pair of complex conjugate roots. Then unfortunately, it does not fall under the case number 1 that we have just illustrated. So in other words, you cannot write this s squared plus as plus 25 as a multiplication of two factors, right? Because the solution for each factor is a complex numbers, then you can't do that. Okay, so you have to leave it as it is. All right. So then that's exactly the case 2 that we're talking about when y of s has complex conjugate poles. Now it does have a complex conjugate poles. Okay. If this happens, then the next state you need to do is, okay, you still want to simplify it into the simplest form so you can actually look up the table from, right? So let's do that. S plus 3, we treat it as very much the same what we did in the case 1. Okay, so I'm going to have a fraction which has a denominator s plus 3. So a over s plus 3. And for the second term, s squared plus as plus 25, we're not going to change it. We're going to leave it. This is the fraction, the denominator of second fraction. The numerator here, okay, and this is where you have to remember, the numerator has to be bs plus c. Okay, the numerator, and it has to be 1 order less than the bottom. This is second order here, so that's why it's a first order. Okay. And there has to be 2 terms, and so b times s plus c. So if I had to emphasize, the reason you put a bs plus c at here, okay, let's call this as a rule. Okay, this is a rule at here. The rule is if you have a second order on the denominator, then the numerator has to be bs plus c. This is how you will deal with y of s if it has complex conjugate roots, okay, from the denominator. And this is how you would decompose it into two terms. We call it simplest because that's basically the simplest you can go. Okay. Of course, now the question is, next is what's A, what's B, and what is C? Okay. So for this approach, we actually can use, again, this comparing coefficients approach. Okay. So I'm going to use the comparing coefficients. So to use comparing coefficients, so here's your y of s, right? So what we need to do is we need to write it back into one single fraction. So we write it back into one single fraction. Then we can compare coefficients for the numerator. And there's no trick here. You just basically write it back into one single fraction. And this is your numerator at here. And you need to simplify it first. Okay. Simplify means you group all the terms with the same factor. In this case, we group all the terms associated with s squared. Okay. It turned out to be a plus b for this one. We also group all the same term for the s term, which is 8a plus 3b plus c. And lastly is the constant term. Okay, right. So that's once you put it back, calculate carefully, and you get the y of s in terms of all the unknown constants a, b, c. Okay. So now you compare coefficients, right? Compare coefficients. What are we comparing? What's the original coefficient? 20. So you compare basically with 20. Okay. So if I compare with 20, first compare coefficients associated with s squared, which is a plus b. And coefficient for s squared on the other end, there's nothing, so it's 0. And then compare coefficient associated with s. That's 8a plus 3b plus c. And again, it's a 0 because there's no s terms on the right side. The last, compared the constant terms, 25a plus 3c should equal to 20. So 3 equations, 3 unknowns. Okay, they're all linear. You should be able to solve for a, b, c, which is 2 for a, b is -2, and c is -10. So that's the result of comparing coefficients. Okay, good. So now the y of s equal to 2 over s plus 3, and then plus -2s minus 10 over s squared plus 8s plus 25. So watch out for the next step. It's actually tricky ones here. So then the next step is to get the inverse Laplace. So inverse Laplace, you have the inverse of these two terms over here. The inverse of the first term, it's pretty simple. So 2 times e to the power of -3t, and then multiply by u of t. Okay, so this is clearly given by the table. So the question basically is, what is the inverse of second term? Okay. So this one is not so obvious. It's not so obvious. Because why? If I look at my table here, okay, if I look at my table here, so which one should I use then, right? So if you look at the table over here, I'm not going to use this because there's only two terms here. And there's nothing to use here, there are only two terms. So if you look at the denominators for this table, the only closest is these two, right? Is these two. So you look at these two here. Can somebody tell me what is the root? What is the root or pose, okay, for these two expressions? They're the same thing, right? The denominator here is the same thing. So if you look at this root here, s plus a square plus omega square, you set equal to 0. What do you think the roots for this s is? Do you think it's a real number, or do you think it's something else? It's complex, right? So that's actually what we're having now, right? Because our denominator s squared plus as plus 25 give you complex conjugate roots, and this s plus a squared plus omega squared, it give you also complex conjugates. Okay, so that give us a hint. I should write my current expression from the denominator to be the same format as this s plus a squared plus omega squared. So then I can use the table here. Okay, so basically the term over here needs to be rewritten to match the table. Okay, so let's try this and here, and let's see how can I. So how to. Basically, the question is how to write that s squared plus as plus 25 into a format of this. So let's do a little bit of reverse engineering, okay? So for this term here is s plus 2as plus a squared plus omega squared. Now, if I need to write that term into this, so clearly you can see the 8 should equal to 2a, and 25 should equal to a squared plus omega squared. So that gives you a equal to 4, and then omega squared equal to what? What's omega squared? Plugging 4 here, 16, 25 minus 16, so omega squared equal to 9. Okay? So meaning the s squared plus 8s plus 25 is s plus 4, then plus 9, okay, or 3 to the power 2. Okay? So basically, a here is 4, omega here is 3. So your best bet, right? If you look at this, your a here is very easy. A is just half of that coefficient 8. So that's where you get a 4. And then you solve for the omega using the rest of the expression. Okay. So then the term, I'll just write this term here, negative s over 10, s squared plus 8s plus 10 became s plus 4 squared, then plus 3 squared. Yes. Sorry, come again? Yeah. Oh, why not omega negative 3? Yeah, omega has to be a positive here. Yeah. So you had to write a positive omega. Okay. Yeah. Good. So coming back to the expression here. Okay. So for now, we're an inch close to the expression over here. My denominator match what's in the table now, right? So now the question is the numerator. If I need to use the table, the numerator also has to match the table. So here the numerator is s plus a, the same as this s plus a down here. The numerator is omega, which is same as that omega down there. Now, so let's go back to this. So currently, I don't have a match to the table, right? So the next question is, how can we manipulate the numerator so that we can match the table? Right? So this is what we do. I'm gonna manipulate this table here. Okay. So remember, if I want to use this, this has to be s plus a. So basically means I have to have s plus a term on the numerator. So this is s at here. So then maybe, okay, I'm going to put a negative sign out of it. So negative, put a big bracket because I put a 2s at here, 2s plus 10. I'm going to change the s to s plus 2 because I need that to be the same term, s plus 2. Okay. If I change this s to s plus 2, so then what's the effect for the constant 10? So this is 2s plus 8. And then the constant 10 instead of 10 is now it should be what? Plus 2. Okay, good. So now I got s plus 2 on the numerator, right? So then take the negative 2 out. So I will have the first term here. So this is the first term. And then you have the second term over here. Two fractions. First fraction is two s plus 4 divided by the denominator. And the other term is 2 over s plus 4 plus s squared. Okay. And then there's big negative sign in front of it. Any questions so far? Yes, very good. Oh, it's not s squared, so it's 3 squared. Yeah. Good. It's all good? Okay. So can somebody tell me what would be the inverse Laplace of the first term? You look at the table here. You already have exactly matched the table now, right? So the inverse Laplace, A is 4, S is 3. So you can actually get the inverse. But the second term here, it's not quite there yet. The numerator is 2. If I need to use the table, what should the numerator to be? What the numerator should it be? Numerator should be omega should be 3. So let's put a 3 here. If I put a 3 at here, then what do I have to do? Multiply by 3. Right? So this way, we're not changing anything at all. We're just manipulate it to be the same as what's given in the table. So then the inverse Laplace, right, of negative 2s plus 10 divided by s squared plus 8s plus 10. Okay, so you look at these two terms, the inverse Laplace, it should be negative 2. The first term is e to the power negative 4t and cosine 3t. So cosine omega t. And the next one is 2/3 times e to the power negative 4t and then sine 4t. So technically you should multiply everything with u of t just to make sure indicate this is a causal function. Okay. But that's the end of it, right? So this is your inverse Laplace of the second term, which contains the complex conjugate roots. Okay. So this is case number 2. So let us thinking a little bit here. The trick, right? I find the difficulty always, okay, let's go back to the question I used when we have 30 seconds to review. The trick, when you have an expression, initially you have an expression over here. First step, you need to be able to identify that you actually have complex conjugate roots. Okay. How do you do that? You just have to solve this one to see what the roots is, right? Use your calculator, whatever. Once you identify that, then you can write this y of s or decompose it, right, according to this way. There's no other way. There's only this way. You have to decompose it like this one. And the next step is to compare coefficients to get all the constants. Once you get the constant, the last step is probably needs very sharp eyes, right? Is how you can manipulate it to fit into the table to find the inverse. Is that good? Yeah. So that's the case number 2's general procedure. So there is one more case, but I think I probably can skip that. So I'll talk to the instructor. So we'll look at a couple examples from in the next lecture, okay, in terms of how to relate to the solution of second order differential equation. Any questions? Yes, sorry.